Raycasting. So here is this example where the chopper is flying up and down in the hangar and the smoke particles only appear when the chopper happens to be near the ground. And the question is, how would you make this? Of course, there are plenty of different ways, but here we're going to try to do it with something called raycasting. To understand what is raycasting, we have to first understand what are rays. For that, you might remember that we have already learned line segments. So line segments are these finite length lines where there is a start position and we can also define an end position. So here the start position is A and the end position is A plus t times t, and well, the parameter t has to be from 0 to 1. Another example is just these lines that are infinite from both ends. Here we have exactly the same formula. We have a starting point A, we have the direction vector d, and all the points on the line are represented as a plus tt. The parameter t can be any real number. If it's negative, then we are behind the point A, and if it's positive, we move forward from point A in the direction of t. Rays are kind of in between the line segments and lines. It's exactly the same equation again. We have a plus tt, but now t can only be a positive real number. So we cut off the negative part of the line, leaving us only with the positive part in the direction of t, and that is a ray. It starts from point A and it shoots in the direction of t. It's perhaps a bit better if we name the starting position start or S instead of just A. And now the example we had where the smoke particles appeared only when the chopper was near the ground can be done with raycasting. So we shoot a ray from the bottom of the chopper down. We find the first intersection with the ray and the ground could be any shape here. And if the distance is lower than some threshold, then we spawn some smoke particles. Now our 3D world is composed of triangles, so we need to solve a ray triangle intersection testing in order to find where does the ray hit our scene. And one algorithm to do that is this Möller-Trumbore ray triangle intersection test. First we're going to define a ray, so this is our starting position plus t times d, and it looks like this. And then we're going to define our triangle. So a triangle, we have 3 vertices a, b and c, and we take 2 vectors from point A to B and A to C. Let's call them E and F. And all the points in our triangle can be represented by this formula now. We have A plus some U times E plus some V times F. If we would write this out, then we would actually see that these parameters U and V are going to be the barycentric coordinates of the vertices B and C. So imagine if both of them are 0, then we are at point A. If U is 1 and V is 0, then we take 1 times E from point A, we end up at B, and similarly with V. So if V is 1 and U is 0, then we end up at point C. You might be asking that there were 3 barycentric coordinates, so where is the third one? And actually it turns out that the third one is just 1 minus U minus V. So even though there are 3 barycentric coordinates that we learned before, there are actually only 2 degrees of freedom if we want to represent a triangle. Now we're looking for a solution to this equation. We make the equation of the ray equal to the equation of the triangle. And this will be equal for some parameters t, u and v, and we will be looking for that solution. So for what parameters t, u and v, we have a solution that would give us this hit point between the ray and the triangle. So here is our equation again. We have the equation of the ray, we have the equation of the triangle, we equate them, and we will be looking for t, u and v. Let's move all the fixed values to one side. So we know s, we know a, so this we can calculate. And on the other side we have these unknowns, minus t times t, u times e, and v times f. Usually these unknowns are represented in the left hand side and the calculated fixed value on the right hand. And we can create a matrix vector multiplication out of this equation. The values t, e, and f are vectors because we're in 3-dimensional space, so they actually have 3 coordinates. We have this vector of unknowns here, t, u, and v. And the fixed value on the right hand side, well, this is also some location in 3-dimensional space. So we also have x, y, and z coordinates of that point. So let's move this up a bit and let's write it in a bit shorter way. So whenever we write these vectors t, e, and f here, we actually know that this is a matrix. Or when we write this s minus a, then we know that this is a 3-dimensional vector. And of course we don't want to carry this s minus a along all the time, so let's just call it p. Now we have this matrix vector multiplication, this equation here, and we have already solved this before. We could find the inverse matrix of this minus t, e and f matrix on the left and multiply that with p, and then we would get a vector t, u and v. However, we are not interested in the entire solution in one go. We actually want to know t, u and v separately and start calculating them one at a time. Because let's say that in the solution t will be negative. Then we know that the ray doesn't actually hit the triangle. The triangle is on the negative side of the ray, so we can already stop calculating. This is the reason we want to know t, u and v separately, one at a time, so we can have these early exits. There is this technique called the Cramer's rule. So the Cramer's rule actually allows us to calculate t, u and v by calculating these determinants. So on the bottom here, we always have the entire system's determinant. So this is the determinant of the matrix minus t, e and f. This is exactly the same matrix we have on the left hand side here. And up here, we have different matrices or different determinants for t, u and v. There are such determinants where if you are trying to find t, the first unknown, then we replace the first column of that system matrix with p. Or if we are trying to find the second unknown, then we replace the second column with p. And similarly, with v, we replace the third column. You might remember from before, there was this thing called scalar triple product. So if we take a cross product between p and c, and then a dot product with a and that result, then we get the determinant of a matrix formed by a, b and c. So let's replace these determinants with these scalar triple products. Now cross product has this property of anti-commutativity. So if we exchange the order of the arguments for the cross product, then the sign changes. Now we can use this anti-commutativity to get rid of these minuses that we have here. So when we use it for all of these terms, then we exchange the order of the arguments in these cross products and we get rid of the minuses. So now all these values are without the minus sign. There is this interesting property of the scalar triple product called the circular shift invariance, which says that we can actually move these arguments around in a circular way. So we move a to the left and it goes to the right, and then b goes to the left and c goes to the left. So abc ends up as bca, and this will give us exactly the same value as the original calculation. Now we're going to use this circular shift invariance, and the purpose here is to actually optimize the number of calculations we're doing. So right now we have these calculations. We have a bunch of cross products, bunch of dot products, and we see that some of these cross products are the same and some are different. But we can use the circular shift invariance to make more of them the same. So for example, up here this p, e and f, if you use the circular shift invariance, then we can make it e, f and p. And this will be the same f cross product p that is calculated for u. And we can go even further. So right now we have this f cross product e's, but if you look up here, then we have this t dot product p cross product e, and here we have t dot product f cross product e. So if you use the circular shift invariance for all of these four terms, then we end up with just one cross product, e cross product t. And now we have four more cross products that are exactly the same. So now that we have optimized the calculations for t, u and v, we can start finding the different terms here. For example, this f cross product p. Let's call it p. So f cross product b will be p. So this will be our first cross product that we calculate for u and for t. The second cross product is this e cross product t. And let's call that q, and this appears in all these four calculations. And lastly, let's call this system determinant f dot product q as d. And this is actually the optimization that Möller and Trumbore came up with in their paper, that to calculate the ray triangle intersection, we just calculate these two cross products and the system determinant, and then some more dot products as we go along. Now the first thing we might want to calculate is the system determinant. So let's find this f dot product e cross product t. And previously we just called it f times q, but q was e cross product t. Now if we calculate this, then it might give us a positive value, a value near 0, or a negative value. And you might be wondering, well, if it gives a value near 0, then these fractions here don't really compute. There will be a division by 0. And this has a very good meaning, a geometrical meaning. And we're going to try to understand this. So first of all, let's use the circular shift invariance again to move this t outside and take the cross product between f and e. Now this cross product between f and e on a right-handed coordinate system is going to give us a vector that is pointing this way, because our angle here is a clockwise angle, so it will be pointing away from us. And now we're taking the dot product between this cross product of the vectors from the triangle and the direction vector from our ray. So if we move that direction vector over here and see what will the dot product give us, we can see that if this value is positive, then the angle between those two vectors is between minus 90 and 90 degrees. So they will be pointing to the same direction from the plane where the triangle is on. Or in other words, the ray is shooting towards the front face of the triangle. So this means that when we have a hit point, the ray is hitting the triangle on the front face. So let's look at other cases. When this t is near 0, or well, let's say 0, then the angle between those two vectors, the direction vector of the ray and this cross product, is 90 degrees. This means that the ray is actually shooting on the plane that the triangle is on. We don't have just one hit point, well, if you have a hit point at all, but we have infinitely many hit points here. This is why when d is 0, then this fraction that we had before, well, this will give us division by 0, because there isn't just one solution. And the third case we have here is if t is negative. So when d is negative, then the angle between the ray and this cross product is larger than 90 degrees. This means that the ray must be approaching the triangle from behind. So if it is hitting the triangle, it is hitting the back face. Now with ray triangle intersection testing and well, ray casting and ray traced rendering, we might want to have back face culling. If we do, then if this system determinant is negative, then we can already stop the process, because we know that this ray, it's not going to hit this triangle from the front, and if it does, it hits it from the back. And if we have back face culling, then we can ignore that result. So those are the conditions for d. If we have back face culling, then we can only continue when t is positive. Now let's look at these unknowns. Let's say we have found the value for t. And if we have found that this t is negative, then the hit point is behind the ray. So here we can stop the algorithm, because we know that the triangle isn't on the front of the ray, it's in the back of the ray, and we don't care about that hit point. These parameters u and v are a bit more interesting. So let's say that u is negative. When u is negative, then we have a hit point somewhere in this area. And this is outside of the triangle. So if we do not check for this, then what we're actually finding is this ray plane intersection, or even line plane intersection. But we care about the ray triangle intersection. So we only care about the solution that happens to be inside this triangle. So when u is negative, we are not inside the triangle. Similarly, when v is negative, then we are not inside the triangle either. So we are somewhere in this area. Also, when u is above 1, then, well, we're taking this vector e more times than 1, so we go outside of this triangle on this side. And when v is 1, then our hit point is somewhere outside of this triangle in this area. And there is one last condition, and this is this triangle over here. And this happens when u plus v is greater than 1. In that case, we will be inside this triangle, but not in the triangle we're interested in. And you can actually see why these conditions are the way they are if you think about the convex combination. So the convex combination also needed the parameters to be positive and their sum needed to equal 1. And if we have the pericentric coordinates, and u and v are the pericentric coordinates of vertices b and c, and well, the pericentric coordinate of a was 1 minus u minus v, then if u plus v is larger than 1, then this 1 minus u plus v, well, that's going to be negative again. This is why we have to exclude also this area. So let's look at an example of Möller-Trumbore ray triangle intersection testing. So on this example, we have a triangle defined by its vertices A, B and C, and we have a ray with a starting position and a direction vector. So our input is the starting position of the ray, direction vector of the ray, and the 3 vertices of the triangle. And we're interested in, do we have a hit point between that ray and that triangle? Now the first step is to find these vectors E and F. So those will just be vertex B minus A and vertex C minus A. So these will be their coordinates. The first check we discussed was in regards to the system determinant. For that, we need to find Q first. So Q is E cross product D. So we take that cross product and we find Q. And next we can calculate the system determinant by taking F dot product Q. And this is going to give us 50. Well, 50 is larger than 0. So this means that we are not either parallel to the triangle or we're not approaching from behind, but rather the ray is shooting to the front side of the triangle. So we can continue. Next, let's calculate this P by just subtracting the triangle vertex A from the starting position of the ray S. When we have B, we can calculate the parameter V. So V was B dot product Q divided by D. We know D, we just calculated it before, it was 50. We also know Q from before. So now what we can do is to take B dot product Q. When we take B dot product Q, we're getting the upper part of this fraction. So B dot product Q is going to give us 33. And we don't actually need to calculate V yet. We know that V is going to be 33 divided by D. But because it's a fraction, we can check is 33 between 0 and 50. Because if it's below 0, then we know that, well, we need to stop because the fraction will be less than 0. And if it's above 50, then we also know that we need to stop because the fraction will be greater than 1. So the fraction will only be between 0 and 1 if 33 is between 0 and 50. And right now it is, so we can continue. Now is the time to calculate P. We already had Q, so this is the second cross product. This is F cross product B. And we're going to use that P in the calculation of U. So P is over here, and for calculating U, we need to take the dot product between D and P. So this dot product here is going to give us 7. And now we can perform a similar check to before. But here, let's add this 7 to 33. Because if this sum is greater than 50, then we are also outside the triangle. And well, if this 7 would have been greater than 50, then this sum would also have been greater than 50. So instead of checking separately, is 7 greater than 50 and then is this sum greater than 50, we just do one check. And of course we also check against 0. Right now 33 plus 7 is 40 and this is between 0 and 50, so we can continue. The last unknown we're looking for is T. So T is just E dot product P divided by D. We need to calculate this E dot product P. We already know, well, E and P. We calculate this dot product, it's 62. Now here our check is that is it just larger than 0. It doesn't have to be below 1 because the ray goes on infinitely on its positive direction, so we just care about it being larger than 0. Depending on the implementation, you could also consider it okay if it's 0, but then you know that the ray is starting exactly on the triangle. But right now we perform this check, this is true, and we can continue. Now if any of those checks would have been false, then we would have stopped the algorithm early because then we would have known that there is no intersection. And now we can actually calculate the value of T here. So T was this 62 divided by 50, the system determinant, and this is 1.24. And we just need to calculate T to find the intersection point, because the intersection point from the ray is the ray starting point plus T times T. Well, we know the ray starting point, we have now found T, and of course we know D as well, so this is the coordinate where this ray and triangle intersect. And we don't actually need to calculate the exact values for V and U either, because they will give us the same result, so we save on 2 divisions. And this was the Möller-Trumbore ray triangle intersection testing example. From this video, you should now understand rays, their mathematical formulation, so start plus T times direction, their usage in computer graphics, so one example is to cast out from some object and find out how far away the scene geometry is, You can use it similarly in other cases. For example, when you have a first-person game and you want to see is the player looking at some specific object, and if they are, is it sufficiently close? So you would then show a pop-up that press E to open this chest that is right in front of you. Or if you have a shooter game and you shoot a gun and the bullet travels in a straight line, then you can see what does it hit in the scene. So anytime you want to know if some object in the scene or the scene itself is close by in some direction, then you can use raycasting. Raycasting is basically just solving the intersection problem. So we have a mathematical ray and we have some mathematical formulation of our scene, usually triangles, so we solve the triangle ray intersection problem. The Möller-Trumbore algorithm is this optimized way to solving that intersection problem because it optimizes the number of cross products we do, the number of calculations, there are early exit cases, and in the end, if all the checks pass, it will give us the ray triangle intersection hit point.